Okay, I'm back. Pure Maths 1. Um, let's deal with this stuff first. Error correction. In two of my previous videos, I had made a couple of silly mistakes. You remember the problem that you had to solve for lambda where two vectors had a given angle between them. And from that step, what I did, I multiplied through it by 3, and I got something like 9 lambda squared minus 12 is equal to 4 into the root of lambda squared plus 20. I hope some of y'all recognize that error. This lambda squared should not be there. If you multiply by 3, that lambda squared should not have been there. And I think I made an error on one of the problems where you have to prove that two lines are skew lines. I messed up the algebra here, I think. I should have had 7 lambda equal 2, from which lambda is equal to 2 sevenths. I think I had some other number there. So I hope you noticed those errors and you would have corrected them for yourself. I don't get feedback from anybody telling me about, what's going on with the videos. Feedback is good, so I know if there are more errors, let me know. The errors are minimum though, I'm pretty sure. But 1 and 2 just get away. All right, let's get back to trigonometry. My afternoon Pure Maths 1 class. I was not up to speed with the morning Pure Maths 1 class, and they hadn't even touched factor formulae, so I'm going to start with that. This would be good revision for the people who are in the morning class. So without further ado, let's go. We're going to derive the factor formulae from the standard compound angle identities. And I've written all 4 of them here, all 4 compound angle identities right there. We should know them by heart by now. And to get my factor formulae, what I'm going to do, I'm going to add and subtract that the first pair, equations 1 and 2, and then I'm going to add and subtract the second pair. So let's do that. Let me bring this up a little bit. If I add equations 1 and 2, I'm going to get an equation that says sine of a plus b plus the sine of a minus b is equal to 2 sine a cos b, and the 2 last parts will cancel out. When I add cos a sine b to minus cos a sine b, that will cancel out. If I subtract them, I'll get the sine. If I subtract them, I will get the sine of a plus b minus the sine of a minus b is equal to the 2 first parts will cancel out. Sine a cos b minus sine a cos b will cancel out. And cos a sine b minus a minus cos a sine b will give me 2 cos a sine b. I'm going to do something similar with the second pair of equations, equations 3 and 4. Let me pull this up a little bit more. If I take equation 3 and 4 and do the same thing, I'll get cos of a plus b plus cos of a minus b is equal to 2 cos a cos b. The sine a cos b, the minus sine a cos b and the plus sine a cos b will cancel out. And if I subtract them, I will get cos of a plus b minus cos of a minus b is equal to, I'm subtracting, so the first 2 parts will cancel out, and I'll end up with minus sine a minus 2 sine a sine b. So what I'll do now, I'll summarize them. Those first 4, if I make the right hand side, I'm going to get rid of the 2's from the right hand side. I'm going to switch sides. So the first one will say this one right here. I'm going to make sine a cos b the subject. Sine a cos b is equal to a half into sine of a plus b plus the sine of a minus b. I'll take the second one, this one, and make cos A sine B the subject. Cos A sine B is equal to a half into sine of A plus B and sine of A plus B minus the sine of A minus B. Should be a minus sign there. Then I'll take the second two and do the same. From this one, I'll make cos A, cos B the subject. Cos A, cos B is equal to a half into the sine of A plus B I'm messing up. I did that one already. Yeah, sorry. Cos A, cos B. Cos A, cos B is equal to a half into cos of A plus B plus cos of A minus B. And the last one, sine A, sine B. Sine A, sine B is equal to minus a half into cos of A plus B minus cos of A minus B. Okay, these are the first four factor formulae. And what these do, they take a product and convert it to a sum. So these are referred to as the product to sum factor formulae. Product to sum. You're taking two trig expressions that are multiplied by each other, and you convert it into a sum or a difference if you want. Product to sum or difference. Right? You're subtracting as well. We'll get four others where we take the sum or a difference and convert it to a product. Here's what I'm going to do. I'm going to take the four formulae up here. These four. 1, 2, 3, 4. And I'm going to make a certain substitution in there. So let me first write them back. Give myself a little space. I'm going to write them back as sine of A plus B is equal to, sine of A plus B plus the sine of A minus B is equal to 2 sine A cos B. Sine of A plus B minus the sine of A minus B is equal to 2 cos A sine B. Cos of A plus B plus cos of A minus B is equal to 2 cos A cos B, and cos of A plus B minus cos of A minus B is equal to minus 2 sine A sine B. Now what I'll do, everywhere I see A plus B, I'm going to substitute P for that. And everywhere I see A minus B, everywhere I see A minus B, I'll substitute Q. So if we let A plus B be P and A minus B be Q, and what we're going to do, we're going to add and subtract this as well. So if we add these two equations, we'll get 2A is equal to P plus Q, which makes A is equal to P plus Q upon 2. And if we subtract, we add it there. If we subtract, we'll get 2B is P minus Q, from which we can say B, excuse me, oh my God, is equal to P minus Q upon 2. Okay. And then we'll substitute back into these four formulae right here. Everywhere we see A plus B, we'll put P. Everywhere we see A minus B, we'll put Q. Everywhere we see A, we'll put P plus Q over 2. And everywhere we see B, we'll put P minus Q over 2. If we did that, we're going to get 4 additional factor formulae that look like this. Sine P plus sine Q is equal to 2 sine of P plus Q upon 2 times the cos of P minus Q over 2. The next one, the sine of A plus B, sine of P rather, my. Sine P minus sine Q is equal to 2 sine 2 cos. This is the second one I'm substituting into that one. Sine P minus sine Q is 2 cos of P plus Q over 2 times the sine of P minus Q over 2. The third one, cos P plus cos Q is equal to 2 times the cos of P plus Q over 2 times the cos of P minus Q over 2. And the last one, cos P minus cos Q is equal to 2 times minus 2 times the sine of P plus Q over 2 times the sine of P minus Q over 2. These 4 are also called the factor formulae, but they convert from a sum or a difference to a product. So factor formulae converting from a sum or difference to a product. Okay, so let me double check, make sure my formulae are correct. The first 4, where are they? Sine A cos B nope, first 4. Sine A sine B. Sine A sine B is minus a half into cos A plus B minus cos A minus B. Cos A cos B, half into cos of A plus B, cos of A minus B. Sine A cos B. Sine A cos B is a half into sine of A plus B plus the sine of A minus B. And cos A sine B, half into sine of A plus B minus cos of A minus B. Good. And the last four, of course. Cos B, sine P plus sine Q, cos P plus cos Q. Alright, the first one, sine P plus sine Q, 2 sine of P plus Q over 2, cos of P minus Q over 2, sine P minus sine Q, 2 cos of P plus Q over 2, sine of P minus Q over 2, cos P plus cos Q, 2 cos P plus Q over 2, cos P minus Q over 2, cos P minus Q, minus 2 sine. Yes, okay. All right, so those are your 8-factor formulae that you can use to your advantage to solve certain trig equations. Now we're going to bring them to the fore a little later on. I also here want to show you the general solution technique that's used to solve trig equations. Now remember back in the day, that's over the Christmas break, only a couple months ago. What we would do is we had the cast diagram technique method for solving a trig equation. The general solution technique does not make us make us convert. Remember, or if we had a compound angle to work with, we had to change it to a simple angle, find all the solutions in that value, and then convert back to the angle that you wanted. General solution technique takes care of all of that without having to do that conversion. Here is the general solution, basically. The general solution technique can be used to solve a trig equation. And note, in every case where I have alpha, alpha may represent a compound angle. So we start off by saying, if we have a sine equation, sine alpha is equal to C, alpha is equal to sine inverse of C. And whatever value you get there, you call that your principal angle. This general solution will be written as alpha is equal to n pi plus minus 1 to the n times the principal angle. N can take on any value, positive, negative, integers, or 0. All whole numbers, both positive and negative and 0. In degrees, alpha is 1/8 to n plus minus 1 to the n times p. Okay. If you have an equation that says cos alpha is equal to c, alpha would be equal to cos inverse of c. And you call that p your principal angle. And then you can have your solutions, your general solution in either degrees or radians. In radians, alpha would be equal to 2n pi plus or minus p. In degrees, alpha would be equal to 3/6 n plus or minus p. The third one, if tan alpha is equal to c, then alpha is equal to tan inverse of c, which you again call p your principal angle. Once you have your principal angle, you can now try to write your general solution. The general solution would be alpha is equal to n pi plus p. N pi plus p if you're working in radians. And if you're working in degrees, alpha is equal to 1/8 to n plus p for degrees. So once you leave your solution in terms of n, that is called your general solution. BRB. Okay, so here's our first problem. Find the general solution, and they gave you an equation with three parts. Sine 2x plus sine 3x plus sine 4x is equal to 0. Now, what we want to do with an expression like that is to convert those sums into products. Because if you have the sum of a bunch of things equals 0, there's not much you can do with that. But if you have the product of a bunch of trig expressions equals 0, then you can put each part of the product equal to 0. So what I'm going to first do, I'm going to group together the sine 4x and the sine 2x. Those two parts. If you think about it, if we use the factor formula in that, the factor formula converts sum to product. And that would be sine p plus sine q. Let's see what that's going to give us. Sine p plus sine q as you remember is equal to 2 sine of p plus q upon 2 times the cos of p minus q upon 2. Right? Sine p plus sine q should be somewhere up here. Sine p plus sine q, there it is. Okay. So I'm going to add together the sine 4x and the sine 2x. Sine, I'll let the p be the 4x. So sine of 4x plus the sine of 2x is equal to 2 sine of 4x plus 2x upon 2 times the cos of 4x minus 2x upon 2. If you simplify that a bit, you'll get sine of 4x plus the sine of 2x is equal to 2 times the sine of 4x plus 2x is 6x upon 2, which gives me 3x, times the cos of 4x minus 2x is 2x upon 2, which is just x. So back in my original equation, I'm going to replace the sum of these two parts with this new expression that I have. So therefore, sine 2x, I'll write the sine 4x next to it. In fact, I'll write the sine 4x first. Sine 4x plus the sine of 2x plus the sine of 3x can be written as, this first part will be written in its new form, which is 2 sine 3x cos x plus sine 3x, and that must be equal to 0. That new expression must be equal to 0. If you notice, we have a common factor of sine 3x on the inside. Sine 3x into, what's left inside? 2 cos x plus 1. And that must be equal to 0. And therefore, we can either say sine 3x is 0 or 2 cos x plus 1 is 0. From which we get, this one will give me cos x is minus a half. And now we're going to invoke the general solution technique on each one of these. So let's see. Nice. I like how one part has a component angle and the other one doesn't. So let's find a general solution for sine 3x first. If sine of 3x is equal to 0, that implies that 3x is equal to sine inverse of 0, which is 0, which is my principal angle. And therefore the solution would, remember, this would represent your alpha here. And if you go back up to the solution for sine, the general solution for sine, it says alpha must be equal to, and be working in degrees here. Alpha would be 1/8 to n. Alpha, of course, is represented by the 3x. 3x is equal to, let me actually write the generic thing. Alpha is equal to 1/8 to n plus minus 1 to the power n times p. Alpha is represented by 3x. So 3x is equal to 1/8 to n minus 1 to the n, and the principal angle, you remember, was 0. So that disappears, which makes x equal 1/8 upon 3. That's 6 to n. That's the general solution for that first part. And for the second part, which says cos x is minus a half, cos x is equal to minus a half, which makes x equal cos inverse of minus a half. I have a feeling, I don't know that one offhand. Let's see. Cos inverse of minus 0.5. (133.3 degrees). Yes, 133.3 degrees. And you remember the cos general solution. The general solution for cos is alpha is equal to 3/6 to n plus or minus p. Well, alpha is just represented by x in this case, right there. That was a simple angle to begin with. So x is equal to 3/6 to n plus or minus the principal angle, which is 133.3 degrees. And therefore, my overall general solution is made up of two parts. The general solution is represented by x is equal to 6 to n, and x is equal to 3/6 to n plus or minus 133.3. That's your general solution, right there in that box. And n is, it could be any positive integer, any negative integer, or it can be 0, any whole number. N is a member of the set of whole numbers. I don't remember the symbol for that offhand. Somebody can look it up for me. All right, either positive integers, negative integers, or 0. Okay, solving three equations using the class diagram technique, using the general solution technique. Well, I just did one using the general solution technique. Here's what I'll do. I'll solve this one using the general solution. Notice, you can solve using the general solution technique. You'll first find, if you're using the general solution technique, you'll find the expression in terms of n. You'll find the general solution, and then plug different values of n into that general solution to find the specific solution. I'm going to do it both ways to show you that it works, and it works really well. All right, so why don't I start with the class diagram technique? I know y'all are very familiar with that. So I'm going to start by letting the 2 theta plus 30 be equal to alpha. Let 2 theta plus 30 be alpha, and therefore the equation becomes sine alpha is equal to half, and you're solving it for the domain theta be 2. No, you gotta change it. You gotta change the domain as well. I'm forgetting my class diagram technique. We're gonna make theta the subject. We know that theta is equal to alpha minus 30 upon 2. So therefore, alpha minus 30 upon 2 has to be between 0 and 360. Multiply through by 2, you get alpha minus 30 is between 0 and 720. And then if you add 30 throughout, you get 30 less than or equal to alpha less than or equal to 750. So that's the new range. So at this point, you're solving the equation that says sine alpha is equal to half for alpha between 30 and 750 degrees. So let's solve that. I don't know what I wrote there. And 750 degrees. Okay, so find the principal angle first. Alpha is equal to sine inverse of a half, which is 30 degrees. That's my principal angle, and it's a solution. Now I need to use my cast diagram to find all the solutions within the given range, within the given domain. So what do I do? Set up my diagram. Draw this as neatly as I possibly can without a C-A-S-T. I need to identify the quadrants in which the solutions must lie. The solutions must lie in the quadrants where sine is positive. How do I know that? Because this equation is telling me that the sine of the angle must always be positive. So I need to land in the quadrants where sine is positive. That would be A and S. The principal angle tells me always make an acute angle of 30 degrees with the x-axis in those two desired quadrants. And the range tells me I must keep measuring my angles, always going anti-clockwise. Positive angles, anti-clockwise. So this first solution is 30 degrees. Let me make this thing look a little more realistic. All right. $30 degrees here. The next one would be in this quadrant, making 30 degrees with the x-axis. So that's 30 and 150. The next one will be, I'll draw another cast diagram. I know I have to land in these two quadrants still. The next one will be a full rotation back in A, where that's 30. The next one still must land in these two quadrants. The next one must be a full rotation and back in S. That's 30. I don't know if I've exhausted them as yet. Let's see. The first one is 30 degrees. Next one is 150 degrees. Next one is 360 plus 30, which is 390 degrees. The next one is 360 plus 150. 360 plus 150, yes, is 510 degrees. It's 510 degrees. I think I am allowed to go all the way up to 750, so I should have at least one more. Let's see. Drop another cast diagram here. Boy, can't draw to save my life. And the next one will be two full rotations. 1, 2, and then back into the L quadrant. Well, where that acute angle there is 30 degrees. Two full rotations is 360 plus 360. And then plus 30 will give me 720 and 30, 750 degrees. Yes. So I think I just made it. So let me summarize all the values for alpha. Alpha, 30 degrees, 150 degrees, 390 degrees, 510 degrees, and 750 degrees. 1, 2, 3, 4, 5 solutions. But the solution to the problem requires that you find theta. And if you look at the conversion, theta right there. Theta is alpha minus 30 divided by 2. To find each value of theta, you take alpha, you subtract 30, and you divide by 2. Okay, so let's see where this takes us. When alpha is equal to 30 degrees, theta is equal to 30 minus 30 over 2, which is 0. When alpha is equal to 150 degrees, theta is equal to 150 minus 30 over 2. That looks like 60 degrees. Need some more space. When alpha is equal to, what's the next alpha? 390. Theta is equal to 390 minus 30 over 2. That's 360 over 2, which is 180. When alpha is 510, theta is equal to 510 minus 30 over 2. I have no idea what's 510 minus 30. I can subtract. 480 divided by 2, which is 240 degrees. And when alpha is equal to 750, theta is equal to 750 minus 30, which is 720 over 2, which is 720 minus 30. 750, man. What's wrong with you? 750 minus 30 over 2. 720 over 2, which is 360 degrees. Wonderful. So let's summarize. For the equation sine of 2 theta, where is it? Sine of 2 theta plus 30 equal to half. To solve for theta between 0 and 360, these are your solutions. Theta is equal to 0 degrees, 60 degrees, 180 degrees, 240 degrees, and 360 degrees. Can we get the same solution if we go through the general solution technique method? Well, we'll see shortly. Be right back. Well, let's see. Let's apply the general solution technique up front, find the general solution, and then plug in the different values of n into that general solution to get the specific solution within the given range. So here's the same equation, and you're solving for that range, but you're going to use the general solution technique. The general solution technique requires you just sine inverse the other side. So 2 theta plus 30 degrees is equal to sine inverse of a half, which is 30 degrees, which is my principal angle. Okay, general solution technique says if you're working in degrees and you want to write down the general solution, then the general solution, what did I do? There we go. Then the general solution, would be alpha is equal to 180n plus minus 1 to the n times p. Alpha in this case is the entire 2 theta plus 30. So 2 theta plus 30 is equal to 180n plus minus 1 to the n. In this case, p is 30 degrees itself. And from this, I'm going to find an expression for theta. 2 theta is 180n plus minus 1 to the power n times 30 minus 30. I can factor out from that 30 and then divide by 2 at the same time. So theta is equal to 30 into 30 by what will give you 118, 6, I think. 6 3 is 18, yeah. 30 into 6n plus minus 1 to the n, and then minus 1. And then you divide that by 2. So finally you end up with theta is equal to 15 into 6n plus minus 1 to the power n minus 1. This is the general solution written in terms of n. N is a member of a set of whole numbers. That's the general solution. If you want to find a specific solution within a given range or a given domain, you simply plug in the different values of n. So what values of n am I going to use? Let's see. If n is 0, anything to the power 0 is 1. So let's start with n equals 0. Let's see what happens. When n is 0, theta is equal to 15 into 6 times 0, that's 0, plus minus 1 to the n. Minus 1 to 0 is 1. Anything to 0 is 1 minus 1. So theta would be equal to 0, and that's yeah, that's a solution. Let's 15 into 0 plus 1 minus 1 is 0. 15 times 0 is 0, which is a solution. Then go to n equal 1. Theta would be 15 into 6 times 1, which is 6, plus minus 1 to the 1, that's still minus 1, minus 1. Minus 1 minus 1 is minus 2. 6 minus 2 is 4. 15 fours, that's 60 degrees. Seems to be working quite nicely. Let's see if we can get the other solutions. N equal 2. When n is equal to 2, theta is equal to 15 into 6 times 2 plus minus 1 to the power 2 minus 1. Minus 1 squared is positive 1. 1 minus 1 is 0. 6 2 is 12. So inside the brackets I have 12. 12 by 15 is 180. That's pretty good. N equal 3. Theta is equal to 15 into 6 times 3 plus minus 1 to the power 3 minus 1. What does that give me? Well, the 6 3s is 18. Minus 1 cubed is minus 1. Minus 1 is minus 2. 18 minus 2 is 16. 15 times 16 should give me 240 degrees. And with n equal 4, I'll get theta is equal to 15 into 6 times 4 plus minus 1 to the power 4 minus 1. Minus 1 to the power 4 is a positive 1. 1 minus 1 is 0. 6 4 is 24. 15 by 24 hopefully will give me what I'm looking for, 360 degrees. Wonderful. So we have two different methods of approaching any problem, really. You can find the general solution and then find the specific sets of solution, specific set of solutions from that general solution, or you could go back to the cast diagram technique that we've been using. All right. I'm going to stop this tutorial here. And I'm going to have more problems for you pretty soon. All right, that's it for this tutorial.